Thank you, David, and thanks to all of you for coming out tonight. I'm very happy to be here. It's my first time at Trent University, so thank you to Trent University for hosting this talk. I thought a lot about how I would start this talk. Obviously, as David said, I wrote a book, Dots and Lines, and that book is aimed at the general public, so not necessarily mathematicians, although mathematicians can read it. And I landed at this idea: the night sky. It's something that all of us know about, look up at. In fact, through the window, even though there's some clouds, I can see the sky here. One of my first memories was looking up at the night sky. I must have been maybe 5, 6 years old, and I could see these lights in the sky. At the time, I didn't really know what they were. They were stars, but I saw these lights and I saw these patterns. And of course, one of the most prominent patterns, at least here in North America, that we see is the Big Dipper. Right, part of the Ursa Major constellation. Now, the Big Dipper is interesting. It looks like a cup, sometimes called the plow. It appears to our eyes that the stars of the Big Dipper are close, that they're very close in the sky, and they are relative to their position in the sky. But in fact, they're anything but close. The stars in the Big Dipper with their distance to Earth in light years. So we have the various stars. I can't see with my pointer, but you see, for example, this top right, Dubhe, which is 124 light years, very, very distant than, say, Merak, which is right below it at 79 light years. So even though they appear very close, this is an illusion. This is an illusion. The stars are actually in three-dimensional space, and they're spread out quite a bit. So the sky reveals networks to us in several different ways. The first way that I'm going to talk about in a little bit is this idea of embedding, of network embedding. What we have are stars in 3 dimensions, three-dimensional data, as it were, and we're mapping it onto this 2-dimensional night sky. So from 3 dimensions, we go down to 2, and therefore we have the constellations in the sky. The other way that we see networks in the sky is from a soup of chaos of the patterns in the stars. And from that chaos, we can see constellations, structures, patterns, lines, and dots. All right, so I should talk to you a little bit about what networks are. So commonly, the word network is also used with graph. Right? Graph theory is a theoretical study of networks. Interestingly, when I was writing the book, I didn't know this. I've been working in the field of network science for 30 years, but network comes from the synthesis of the words net and work. It's sort of obvious staring at you, but I've never really thought of it that way. And what are networks? They're simply just dots and lines. So the dots could really be anything. For example, here on the left, this network, it just is an abstract network with the dots represented by the black circles and the various lines connecting them in this nice symmetric pattern. It doesn't have a representation of anything in the real world. It's just a nice picture. But to the right of that, probably you know what that is, if you can see it. It's a representation of the game Sudoku, right? So you have rows and columns, 9 rows and columns. There has to be the numbers 1 through 9 appearing exactly once on every row and every column. And also every 3 by 3 square, you have to have different colors. So to a graph theorist like myself, this is what we call a 9 proper coloring of the Sudoku graph. And next to that, you see the airline network. So these networks appear in lots of different contexts, lots of different arenas. Now, networks have been around for a very long time. I'd argue they're one of the most basic things that we have in mathematics, next to things like numbers and geometry. But really, you can trace the field of graph theory to one paper. That's the paper of Leonard Euler solving this Königsberg bridge problem in 1736. So hundreds and hundreds of years ago, he studied this. If you don't know much about it, on the left, you have a representation of the river Pregel that was going through this town. And the various land masses, A, B, C, you have these lines which represent bridges. The bridges are 7 bridges there. And one of the things that the townsfolk in the town used to do is go for walks at nighttime and try and cross every bridge exactly once. So they'd start somewhere, so maybe at A they'd start, and try and cross every bridge exactly once and come back to landmass A. They tried this, no one could do it. No one can do it, and there's a reason why no one can do it. It's impossible, mathematically provable, and Leonard Euler proved that in his paper, written, of course, in Latin. At the time, it was 1736, of course. But this was the birth, this was the beginning, the origins of the field of graph theory. So my book, like I said, Dots and Lines, it brings things into a more modern focus, and I'll talk more about networks and all their different influences. But the whole goal of what I tried to do with Dots and Lines was to bring networks to the fore. They're often hidden, as David was saying in the introductory remarks. They're somewhere lurking in the background, and I hope by the end of today's talk to make them a little bit more visible to you. One of the things that I mention in the book a lot, and it's a slogan really, I say it a lot, is that networks measure interactions. Networks are a device to measure interactions. This is a slogan that I mentioned several times, and I'm going to keep referencing it throughout the talk. It's a very powerful way of thinking of networks, these dots and lines, and how they connect us and all the things in the world. Now, the network lens is very potent. It allows us to look at a lot of different things at different scales. So I have here some different networks that you would find, like something like a dolphin social network, which has just 30 nodes, okay, so it's a pod of dolphins. And you could also have an airport network, the one in Canada, which has about 518. There are 518 airports in Canada, all connected by different airline routes. It gets larger, though, if you look at something like the US road network. There are over 19,000 of those, and it goes up. There's Wikipedia and Instagram, the neural network, which I'll talk about in a bit, all the way to the web graph, web pages and their links, which is over 130 trillion. So every time you're doing a Google search, in the background, at least part of that 130 trillion are cataloged by Google and come to you in your search. Now, let me ask you, these two networks, do they look different? They're not. They're the same network. They're just drawn differently. So this one on the left looks like a random soup of dots and lines, and on the right, it's a very structured network, kind of tubular network, almost like a donut. And this is part of this field of graph visualization, taking these complex dots and lines and making them pleasing, visual in a way that we can see things, see structure about them. And this leads me to the topic of network embedding, going back to this idea of the night sky with the stars being represented in this two-dimensional sky. So what every network has is something called a feature space. Not to get too heavy with jargon, but a feature space is essentially reality. It's a long list of attributes about whatever kind of network you're talking about. So if it's a network of people, it could be socioeconomic demographics, their age, their race, their profession, where they live, all these attributes, and a long, we call vector, a long list of things. You could also have dots being proteins in a cell, and their different biochemical properties listed as these attributes. Or you could have meaning, semantic meaning, like you have in word networks. But regardless, in all of these cases, the feature space tells us what is real. And it's often hidden. We don't know everything about feature space. So what we try and do is we take a network like I have there, which is the Karate Club network, I can tell you about that later, and embed it in a space that we understand. So something like two-dimensional space like I have in this representation. So you take very complex, high-dimensional data and distill it down into something nice and compact, which we call a latent space. And the latent space is the space that we create as humans to try and understand reality. The way to think about latent space, at least the way I do, is latent space approximates the feature space. We can't know everything about feature space, but we can approximate it by this latent space. And the powerful idea in latent space is that you take this random soup of nodes and lines, you embed it in some dimension, and what you're going to see are nodes may be close in the embedding, close in the latent space embedding, which weren't close before in your other picture. That can tell you about hidden links, hidden connections between the nodes which you didn't anticipate before. So in the diagram I have here, you have one network on the left, just sort of a random network that I drew, and then I embedded it in two-dimensional space, and if you can make out, there are those red lines, those red edges. Those are the ones we're inferring, we're predicting. So this whole field, very powerful in industry, called link prediction, is what's happening here. We infer links, we predict links based on their embedding in this latent space. Okay, let's make it a little more concrete. So I'm talking about, lots of jargon, feature space, latent space, but everybody here probably uses Spotify or something like that, some music streaming service, right? How does it work? How does it, there's an algorithm in Spotify. It tells you, you listen to a song, and then it tells you another song. It gives you another song to listen to after that, right? There's an algorithm embedded in that. It's a very complex AI, machine learning-based algorithm, but one of the things that it does, and they make it very clear on their website, they use this so-called MUSIG, multitask sampling and inductive learning on graphs. They take an over 100-dimensional vector for every song. A long list in this latent space, over 100-dimensional latent space. And some of the things that are referenced there are things like danceability, genre, energy, tempo, even a 8-dimensional vector corresponding to so-called audio characteristics, whatever that is. And it takes all of these songs and it feeds it through this app and it generates an embedding. And that embedding can sort of infer and predict what you like. So if you're a fan of 80s pop, you're listening to the Smiths, maybe it'll give you REM to listen to, I don't know. All right, so that is one application. Another application, Uber Eats. Probably like me during the pandemic, a lot of us use that, probably still using it too much. It's pretty expensive to use it, lots of fees. But one of the things you notice when you use Uber Eats, it gives you recommendations for other restaurants. It gives you also recommendations within a restaurant. If you tried this dish, maybe you like this other one, right? How does it do that? It uses embeddings. So if you go on their website, the Uber Eats blog, there's quite a lengthy technical argument talking about these things called graph neural networks, which I'm not going to get into, but it's this architecture in machine learning that allows you to use graph structure. And very prominent in this is the use of embedding. So they use this sort of characteristics of the food that you like, they embed it in latent space and predict what you're going to eat based on that. Now, the other way that stars reveal networks is in this area called Ramsey theory. And to frame this, I want to use this quote of Motzkin. It's very nice. It says that complete disorder is impossible. And this is really kind of the foundation of Ramsey theory, as we'll see. So anybody know the Triangulum constellation? Not necessarily the most exciting constellation, right? It's a triangle. But it's going to serve a purpose for us. It's going to serve a purpose, and I'll explain as I go. So this is one constellation amongst hundreds that you can name. Now, let's take 6 stars. I conveniently put these 6 stars in this nice pattern. Let's start randomly connecting the stars like we would in a constellation, right? Constellation are dots and lines. Let's start adding some lines to the constellation. So far, there's nothing there. All right, so add this one, the next, another one. Oh, look, I've created Triangulum. So by randomly, and you can say, well, I did this bias, so I didn't want the talk to go over time, so I definitely got Triangulum in there over time, but if you did it eventually long enough, you will always see Triangulum, which is something I'm going to explain to you. Okay, so Triangulum always appears amongst 6 stars. Well, not quite. Triangulum or its opposite, and I'll tell you what that means. Okay, so let's talk about Triangulum and a new constellation that I'm going to call Anti-Triangulum. Maybe not as catchy as Triangulum. Anti-Triangulum are 3 stars with no lines between them. Okay, so that's just, it's almost like nothing, right? Just 3 stars and no lines. Okay, so how does this happen? Why can't you avoid one of these two? Well, you take a node, like this one, this dot, we'll call it X, right? Mathematicians love to call things X that we don't know, so we'll call it X. All right, if you look at X, there are going to be 3 edges at least coming out of X, or at least 3 non-edges. Because if you look at X, there are 5 possibilities of things it could link to. So you either get at least 3 edges out of it, 3 links, or 3 non-edges. Just for the sake of argument, imagine you had these 3 links like this. Okay? You always have at least 3 edges like this, or non-edges. Let's call the endpoints A, B, C. If any one of these is linked, I get the Triangulum constellation, right? I'm done. If any one of those 3 has a link, I'm done. But what's the only other logical possibility? Well, none of them are linked. In that case, you get the anti-Triangulum constellation. So no matter how I do this, and a little bit of leap of faith, because you have to argue also with the non-edges from X, but it also works the same way, you always are going to get one of these 2 constellations. And this is because the Ramsey number R3 is equal to 6. Now, if you did it with 5 stars, it doesn't work. All right, so here are 5 stars, and I've drawn it in such a way, these are the lines of the constellation, right, this sort of pentagram, And the outer ones, the perimeter, no edges at all. There are no triangles, and we don't count this as a triangle. The triangles have to end in dots, right? There is no triangulum, there's no anti-triangulum in this, no matter how you look at it. So 5 doesn't work, 6 does. And this, like I said, has to do with this field of Ramsey theory, which is very old and very austere, very difficult field. So what we just demonstrated really was looking at R3, the third Ramsey number. R3 is exactly equal to 6, and that shows if you have 6 dots and you join them up by lines or non-lines, you're always going to get a triangle or its opposite, an anti-triangle. If you wanted to generalize this to 4, because, again, that's what mathematicians love to do. They understand something with something nice and small like 3. With 4, here are 4 nodes all linked together, right? A clique. Its opposite would be no edges. You have to go to 18. So even if you have 17 dots, 17 stars, you may never see this or its opposite. At 18, you always do. And the amazing thing, those are the only Ramsey numbers really that we know. No larger ones are known. So even the Ramsey number R5, again, you have to see this or its opposite, no edges. All we know is that if you take a graph of order 43, 44, 45, or 46, one of those works. We've narrowed it down to one of those 4. It's the smallest number possible. And you can say throw it in a computer, but there's huge combinatorial explosion. You cannot work out even 43 with the most powerful computers and algorithms that exist. I will mention that there's been some developments in Ramsey theory. So there is a bound. If you don't understand a number like the Ramsey number, you can find these things called bounds, which are telling you how large something can be. So this is a young picture of Paul Erdős and George Sekres. I include these younger pictures because Paul Erdős, the famed mathematician, he discovered this fact when he was 25. So he looked about like that. He showed with Sekres that the Ramsey number Rk could be no bigger than 4 to the power k. So we have some upper bound on how it behaves. Recently, just a couple years ago, it was improved from 4 to the k to 3.993 to the k. And, I read quotes in Quanta magazine about this, mathematicians at Princeton who heard about this result, saying they were shaking for hours when they heard about this improvement after 90 years. And, admittedly, when you talk to non-mathematicians, which is virtually everybody, they're like, big deal, it's 0.007 better, right? But it took 90 years to make this improvement. And in fairness, like you think about this is the base of the exponent. When k is large, there's a big, big difference between these two numbers if k is large. So there's still work going on in Ramsey theory. It just takes decades to make progress. All right, so networks, as we've seen, they show up in things like the night sky, dolphin networks. They come up everywhere. They come up in places you don't even expect. Admittedly, I didn't expect this when it first was studied, the Game of Thrones. So Game of Thrones, probably most of you are aware if you're watching this or you've watched it, or House of Dragon, very expansive fantasy novels and HBO series. What do we know about Game of Thrones? Written by George R.R. Martin, sold 90 million copies of the book worldwide. It's kind of like Lord of the Rings with lots of sex and death, right? And the series on HBO, the finale had 19 million viewers, probably some sort of record, huge number of Emmy awards. The fascinating thing about it is it has 2,000 characters in its legendarium. There's a huge group of characters you can pull from. And why is this interesting to network scientists? I'll explain. So you can form a network from the characters of Game of Thrones in the following way. So maybe you're familiar or maybe not. This one on the left is Sansa Stark, and then this one is Tyrion Lannister, two prominent characters. You can form an edge between these two characters, thinking of the characters as the nodes, if they appear together in the same scene. In a novel, it could be like maybe they're 15 words apart in the text. You see the word Tyrion, you see the word Sansa, 15 words apart or less. In a script, you look at it in a similar way. And they're in the same scene in the show, you can extract a network. So from these 2,000 characters, you can form this expansive network. How do you visualize it? How do you visualize this thing we call the network of thrones? I have to do a little bit of a detour with some mathematics to explain how you do this, because I could just do a random soup of characters that really wouldn't mean anything. So for that, I need this notion, two things, modularity and the Louvain algorithm. So modularity, it's technical, but what I can say is it basically measures the difference between these two pictures. These two pictures, they're networks, you have different colors. The yellow, blue, purple, and red, they're called communities. They're groups of nodes that have a lot of links between them, more links between them than they have outside. So they're more structured, more clumpy networks. Here you have just a big soup with all the colors mixed almost randomly. So this is highly modular, this is not modular at all. Okay, so it's a measure that you can do on any network, you can measure its modularity. There's a formula for it, you can measure modularity gain. And what the Louvain algorithm does, it takes a network and it creates a community for every single node in the network. And it keeps on running modularity when you move nodes between the different communities. So if you take a node and you move it to another community and modularity goes up, you say, oh, that's good, and I'm going to keep that. If the modularity goes down, you undo it. And you keep on doing this iterative process, and eventually you end up with this breakdown into this coloring, a partition of the nodes into these different pieces. Okay, so that's like a admittedly very fast crash course in how the Louvain algorithm works and modularity. Do you want to see the Network of Thrones? Yeah? Okay, there it is. So this was taken at book 3. There are 7 books. This is about midway through the saga. You see many of the characters if you're familiar with this. Oh, and I have to give credit. So Andrew Beveridge, professor at Macalester College in the US, and one of his students, Jishan, published this in 2016. So you see many of the key characters here, like Daenerys, Tyrion, Robert, Robb Stark, Jon, and so on. And again, this was not from reading the book. This was extracting names and constructing a network, running the Louvain algorithm, and coming up with this breakdown into communities. And you can see nice things here. You can see like all the people centered around Daenerys or Tyrion, like the whole Lannister family is here. Well, Sansa, she's being married off and so on. So it's all in there. Not everything, but a lot of things are there. So the network scientists rolled up their sleeves. They did network science. They analyzed various statistics. Some of the fans were very excited. In 2016, they thought, this is fantastic. And it got written up in the Wall Street Journal and lots of things. Other fans, not so happy. They referred to it as nerd slime, right? So, network science, mathematics, you have to be careful. Sometimes people have a negative reaction. They thought basically that by doing this analysis, you're going to ruin the story. I don't think you ruined the story, but you did discover something interesting. So if you've seen the series or watched or read the books, Jon Snow, big character, right? Tyrion Lannister, big character. Now, at the time, around the 3rd book, Sansa Stark, not so important. She was more of a pawn. She was being married off through various houses. She had no agency. But spoiler alert, by the end of the series, she became very critically important, and network science predicted that. So it was a really interesting application of something that actually happened. It was essentially kind of link prediction with who she was connected to and other structural properties of the network. Now, this has also been done for other networks. Lord of the Rings, huge number of characters in Lord of the Rings books. The Marvel Universe has over 10,000 characters, and so there's a huge visualization of this. There's also the Twilight network, so if you know anything about Twilight, admittedly, I'm a bit of a twihard. So you have, the different vampires and their family, Bella, and then some of her high school friends and so on. Also, I'll mention this. So one of my graduate students looked at these longer books, so Lord of the Rings, Game of Thrones, Harry Potter, broke down all the books into chunks of text, treated all the 7 books as one big book, and predicted character interactions. So say, for example, you look at something like Harry Potter, you look at Ron Weasley and Voldemort. They don't appear together in a scene earlier on in the book. But what his research showed using network embedding is that up to 7 chapters, he could predict accurately whether or not they're going to be interacting or not. So again, more nerd slime. All right, we also use this when looking at things like Trump and Trudeau on X. So I had a student, Alex Nazareth, and another one, Linda Abraham, analyze all the texts, all the tweets of Trump and Trudeau around 2020. This was, I think, March 2020, around the beginning of the COVID pandemic. And you can see, I know on the screen it's maybe a little small, pretty big differences in the kind of things that Trump and Trudeau were tweeting about. Like Trudeau had no reference of things like crooked Hillary and so on, which you'll see amongst Trump. But again, using the Louvain algorithm, we were able to parse this, and we extended this to analyze over 600 politicians and patterns in these networks. All right. So it is a small world. We know this. It is a very small world. There's lots of people that we're connected to. Social media has definitely made us keenly aware of this, sometimes painfully so. So I thought I'd give an example to illustrate a small world. I've never met Albert Einstein. I'm too young for that, sorry. So Albert Einstein and I, both scientists, mathematicians, and both published, we can link to each other by collaborations. Not directly, I haven't written a paper with him, but Albert Einstein wrote a paper with someone named Ernst Strauss. And Ernst Strauss wrote a paper with Paul Erdős. Paul Erdős wrote a paper with Peter Cameron, who wrote a paper with me. So I'm only 4 links, 4 degrees of separation from Einstein. So I guess that must mean I'm very special, right? In fact, I am not. Almost all scientists are paths 3 or 4 from Einstein, and I'll talk about that. In fact, if you look at Erdős, so Erdős is the critical node here. Paul Erdős, something like 500 co-authors, huge number of collaborations. He's a hub in this network of collaborations. Almost anybody can link to anybody through Erdős. And if you look, by the way, that's me right there. This is all the people with Erdős number at most 2. If you know about Erdős number 0 is Erdős. People who wrote a paper with Erdős 1. If you wrote a paper with someone who wrote a paper with Erdős, but you didn't write a paper with Erdős directly, if I said that correctly, you're 2. And I'm 2 with Peter Cameron. So a lot of people have Erdős number 2. And if you fan out to 3, it's almost all mathematicians. There's more and more counterexamples as you go out, but if you go out to 10, it's virtually everybody. What about actors in Hollywood? So I don't know if you know this, but Albert Einstein also was a movie actor. Well, he had a cameo role on the phone in a movie in the 1950s called Champagne for Caesar. Things you learn when writing a book, right? So he was in a scene with Larry Steers, who is in a scene with Glenn Ford, who is in a scene with Kevin Bacon. Now, if you've heard of the Oracle of Bacon before, the Kevin Bacon game, Kevin Bacon appears to be a central node in Hollywood. Right, almost everybody either, he's been in many movies and television shows, Kevin Bacon has, very gifted actor. But it seems like Kevin Bacon is the center of the universe. In fact, if you look at the Bacon number now, right, so just, you know, there's only one Bacon number 0, right, that would be Kevin Bacon himself. All the people that Bacon has appeared with, you can see over 2,000 co-authors, collaborators, I guess, co-actors in this network, right? And if you go up to 2 and 3, you see the huge number of people are clustered around 2, 3, and 4. And you have to go even out to 10, you see 40. And when I was doing research for this, I was trying to find people with Bacon number 4. I had a really hard time doing that. It's very challenging even to find 4 and 5. So I don't even know who these numbers are. This is reported on the website, the Oracle for Bacon. Now, this small world property is not something unique to actors or to scientists, mathematicians. If you look on Facebook, for example, they did a study themselves of the interactions, the links within Facebook. And they found a huge number of people had average degrees of separation a little bit below 4. So what that means is you take 2 random people on Facebook, very likely they're going to have a chain of friends, 1, 2, 3, 4, connecting them. Any 2 random people. It makes it seem like we're all intimately connected, and we are. And we're connected in ways which are not always good. An example of this would be Cambridge Analytica, if you heard of this. So this was a big scandal around 2016. Of course, Donald Trump was running against Hillary Clinton at the time. Cambridge Analytica, a UK-based data analytics company, what they did was they put out a personality test. I think over 200,000 people took the test. It's something to do with your digital life. So they asked people questions on Facebook, right? You sign up for this, and when you sign up for it, there's a terms of service that you click on, right? That was the bad part. So people did this personality test, and unbeknownst to them, their data, their personal data on Facebook, and all the data of their friends was released to Cambridge Analytica. That meant 87 million accounts got into the hands of Cambridge Analytica from this 200,000 people taking this personality test. So it was a huge blunder for Facebook. They radically changed their privacy rules, etc. But that just goes to show the perils of living in a small world. Other examples are things like COVID, which I'll talk about later. We're very highly connected these days. The networks are small, but that doesn't always have good effects. All right, I want to turn now to Emily Dickinson. So she wrote a poem called "The Brain is Wider Than the Sky." The brain is really fascinating when you think about it, especially as a mathematician, not as a neuroscientist. 3 pounds, approximately, sitting in my skull. Everything I know, all of my memories, my entire personality is encoded in this 3 pounds. It's the most powerful thing we know, the most powerful computer, if you want to call it that, in the universe that we're aware of. So you can form a network from this called the connectome, which I'm going to talk about. What is a network? So the nodes, the dots, are the neurons, the individual neurons in the brain. And the links between them are electrochemical signals. So they communicate by these electrochemical pulses, and they fire, and they're able to communicate. It's a huge network, the connectome. It's vast. It's so vast. So there are 100 billion neurons with about 100 trillion links, 100 trillion synaptic connections in our brains alone. The number of total connections, if you were to stack all the neurons, they're very small, but if you stack them all together, there'd be 300,000 miles long. That's well past the moon, okay, just from one brain. Also, every neuron can have up to as many as 15,000 links. It's one of the most complex networks out there, and admittedly, we really don't fully understand the connectome. There's a lot of research on it, but there's a lot that we do not know about the connectome. I'll mention just 2 studies, just giving you a taste of it. There was a study, this was, maybe you can't read that, it's from 2018. Several authors looked at it. They analyzed brains of healthy people with MRIs, trying to analyze the networks that they found. And they used this tool called persistent homology from topology. It's this field which basically looks at structures and things and how they're flowing together or not, like these things called cliques. Cliques are highly structured parts of the brain, and there are also things like rings, which are more like parallel processing, don't have as many links between them, but they sort of convey information along these rings. So what they were able to do doesn't seem like a lot, but it was a big deal at the time. They analyzed these brains with MRIs of living people, right? And they discovered that there are more cliques and cycles than you would expect in a random wiring. So just the very beginning of understanding of how our brains are wired. There is a structure there in the connectome. We don't fully understand it, but there is a structure. Another study, this was a little later, I also found this fascinating. Parkinson's, of course, very devastating illness. You know, Ozzy Osbourne was one celebrity who died recently, had, Parkinson's is a very, horrible disease. What they looked at in this study, this was from 2020, they took 14 people with Parkinson's and they gave them an exercise program over 10 weeks. There's sort of anecdotal evidence that exercise helps people with Parkinson's, helps their disease, slows their disease. So what they did was they took MRIs of their brains before and after the exercise. And interestingly, what they found was that after the exercise, their brains were more structured. They had more structure. They weren't as random as they were if they had no exercise. So they became more connected. There were more paths between the different nodes. And locally, they had these clusters. They were more clustered. So again, just the beginning of our understanding of the connectome. I really love to know more about it. I think it's a very active area of research. Now, I'm going to take you through something I've worked on about finding bad guys. Okay, so networks can help us find bad guys, and I have to contextualize this as such a broad statement, but money laundering, if you've heard of this before. Money laundering, like a gang, the mafia, someone could take money they got from, selling drugs or something and put it in a banking system And they just wouldn't put it all in their account and then just take it out. That would be a signal to the authorities, right? There's a lot of money that's moved around. So they start layering it. They start putting it into the system, this process of placement, and they start moving it around the banking system in these different cycles. So, the idea, people thought it was Al Capone with his laundromats. That's the word money laundering came from. That's actually an urban legend. There's no truth to that. But it's a good analogy. Basically, you put money into like a laundromat. Laundromat puts something into a nursing home and then to like a funeral parlor or something, and it moves around. And eventually the money comes back after this cycle, and it comes back to you in a way that you can access to buy your yachts and jets and things like this. So that's what money laundering does, okay, what it's about. Now, I don't have to tell you, money laundering is a big problem. There was a recent incident with TD Bank in the United States. TD Bank had a $3 billion US fine for money laundering. They didn't catch it. I think the Chinese mafia was involved with this. So there's huge penalties. They have very extensive anti-money laundering teams, people who work on this all day, trying to prevent money laundering. But it's very, very challenging. I think in the case of this, there were bribes to tellers and people working in the bank from the bad guys. So even then, the US government took harsh action, and you can see that in Europe and many parts of the world, huge, huge fines, penalties. So banks are keenly aware of money laundering. They want to prevent it. Now, how do we think of networks in terms of banking? One way is to take accounts, individual accounts, like your checking account. Each of those are nodes. And if you make a transaction, like you send money to a friend or your mother, whatever it is, that is an edge. So here, for example, this edge from V to U, it is 8, so I forget what that represents, maybe just a signifier. And then it's the amount of money over the time. So between 2013 and 2020, I know what this is. This was 8 transactions of $30,000 in total from this time frame. So if you have data like this, you can get a lot of information about, how the money is being moved around. There are huge issues with privacy, of course, with banking networks. You can talk to me later how we got access to this data set. It was all above board, but we can't make it public. It's from Rabobank, which is a Dutch multinational. There are 1.6 million accounts in this anonymized data set that we were using, and about 4 million transactions between them. Okay, so we had this access, and this is a representation of a small, I think about 100,000 different accounts represented here in this picture. So what did we do trying to catch these bad guys? Well, we applied the Louvain algorithm. We broke up the network into smaller chunks. Okay. From there, we want to isolate the fast transactions. Money laundering typically doesn't happen over many years, so all the transactions with less than 1 year. And we wanted amounts up to $10,000 or less. Because if you've tried this, if you tried to put a check in a bank account for more than $10,000, it'll be held by the bank. It'll be flagged by the bank. So money launderers are smart of that. They want to prevent that. So we applied this algorithm and detected these directed cycles. Very simple seeming algorithm using existing tools. And here's what we found. So what we found a number of things. In the end, what we found were 83 directed cycles amongst these 1.6 million accounts. And when you think about it, these cycles should be rare. Like, why would you send money 3 or 4 times in a cycle coming back to yourself? That seems sort of strange. That's a signifier, at least to one of our co-authors, Juan Palan, who's actually working for a bank while he was doing his master's with me, so he was telling me all this, although he couldn't tell me much more because everything's hush-hush. 83 cycles we found, and among those 83 cycles, there were 646 flagged accounts. Now, in common in data science, network science, we had no ground truth labels. I didn't know who the bad guys were. But what our research signifies, and yet later on, Adam, who's working with me now as a master's student, he was an undergrad at the time, he's developed another tool with embedding to analyze this deeper. These 646 accounts are places you should look. Okay, so it was like our paper was like proof of concept. Here's a data set, we don't know who the bad guys are, but potentially these are the ones you should be looking at. And right now, banks use very time-consuming, costly things, a lot of ML, a lot of deep learning, trying to determine, who are the bad guys. And we think maybe they should use networks. That would be one shortcut. I don't have a lot of time, but I want to finish on something to do with memes. I was once talking to a student, and I asked him, do you know what a meme is? And he said, of course, I'm 25. right? I guess my age, I'm 54, it wasn't a thing when I was younger, but right now, if you look at my Twitter account full of memes, it is big. Lots and lots of memes out there. So I'll give you an example. So I don't know if you can read this. Anthony Pompliano, no relation. He's a sort of a tech crypto bro, and he did this tweet a couple years ago. I'll read it for you. He says, "The most successful people I've met read constantly, work out daily, are innately curious, have laser focus, etc., etc." You get the idea. And you would imagine in the culture we live in now, he was roasted online, right? Trolled heavily. Like there's a drag queen, Katya, who wrote, "The most successful people I've met are dead, have passed on, are deceased, no longer live," etc., right? And there were literally hundreds of these, right? So Anthony Pompliano's original tweet, which is, I guess, well-meaning, was heavily trolled online. And what's fascinating about it is that it was mapped. There was a mapping on the Twitterverse of how this meme spread. So it's a GIF it'll run through. There's the original Anthony Pompliano node, and we'll watch it from the beginning. It starts to sort of infect, spread to all of his friends, and then Sarah Ito did something, and it spread, and pretty much over time, everyone got exposed to this meme who was on Twitter. Even if you didn't like it or retweet it, you saw it on your timeline. And memes, what are they? Well, you probably, any of you have like Gen Alphas or things like this, young Gen Zs, the 6'7", right? This is the thing that they're shouting out now in math class, right? What are memes? Richard Dawkins introduced memes in 1976. It's this idea that replicates. It's a behavioral scientist idea, but it replicates in culture. So it could be a song, it could be an action, it could be a 6'7" or whatever it is. And it spreads quickly and it pops up anywhere. Those are sort of the key things about memes to remember. And of course, we all lived through this. I'll remind you. So this is a time-lapse photo of the spread of COVID, originally starting in Wuhan, China. And you can see the time up there. It's around early 2020. It's spreading rapidly through China, hit Japan, and I'll wait for it when it hits. Yes, it's just starting to hit Iran and Italy. Those were early places where it went to. And then another big key jump that it makes, it hits New York City, and then LA and so on. Once it hit New York, it basically spread to all over the world. These are transportation hubs. Once you go to New York Airport, you go through the subway system, you've infected a lot of people, they'll travel to other places. So the way we can think of contagion, which is really what memes are, or things like COVID or influenza, you can think of it as a kind of contagion, social contagion or actual contagion. You can represent it very simply as burning. So take a line. We're all in lines in grocery stores during COVID, right? Lines are safer. Lines are safer for us. Why? Why are lines safer? Well, say this person has COVID. Well, I guess the worst case is they could spread it to their neighbors, right? If that person has COVID, I label that one, they could spread to their neighbors with COVID. And then, oh, it's a bad line. Somebody else gets COVID over here, right? And then they're going to spread. And then there's maybe another network, another node that pops up and also has that contagion. And so you see in 3 steps, the whole line will become infected, which is unfortunate. But if you're trying to slow down the infection as much as possible, lines are the best. Lines are the best, and I'll explain. So this burning number, it's sort of the minimum number of rounds. You can't do it in 2 steps. If you chose 2 random nodes and burn them and have them spread, it won't be enough to cover everything. With 3, you can, and that's the burning number of this linear structure with 9 nodes. In general, n, another thing mathematicians like to talk about, n, so n greater than or equal to 2, I guess. If you look at the burning number of this linear structure with n nodes, it's about square root of n. Square root of n, which, okay, so what? That actually happens to be about as best as possible. So there's a conjecture that we formulated, something called the burning number conjecture. In a connected network, the burning number is at most root n. So what we're saying is, like, this is the worst possible. So lines are safer. Lines are safer than things like tables where everyone's connected, right? So there's actually some mathematical theory behind that. It's a conjecture, so it's a vague idea. We don't know how to prove it. With some co-authors, we've got this bound. Hopefully we don't have to wait 90 years to see the proof of the actual conjecture, but it's in the radical 4/3, n plus 1. Again, they look very similar, but if n is large, there's a big difference between these two values. That is the state of the art. This is the best we can do in general. So some takeaways, I'm nearly done. Takeaways, networks give us a fresh quantitative view of the world. They're everywhere, and they measure interactions. You can learn more about it. Read my book, talk to me, follow me on Twitter for great math memes. And before I stop, I want to try a little interactive experiment. Is that okay? All right, so where's Doug? Doug's going to be handing out glow sticks. This is a very important experiment. If we could catch the lights, is that possible? The lights in the room, we want to go pitch black, as close as black as we can. That's good, all right. So Doug is, just be patient. Doug is one person who's handing out the glow sticks. He's going to have some help. Everyone will get a glow stick. Don't do anything with them. I know it's tempting, right? Don't do anything with them just yet. I'll tell you what to do. All right, so here's what we're going to do. So as we get the glow sticks, I'll explain how it's going to work. I'm going to burn you guys. Right? No one is hurt during the filming of this lecture, I promise. So everyone's going to get a glow stick, and I'm going to point to a person to crack their glow stick. Do you remember, from being a kid, remember not so long ago what glow stick, how they work, right? You just take the glow stick, you crack it. Don't do it yet. Don't do it yet. You crack it, and you shake it, and it glows, right? You shake it, and it glows. So does everybody have a glow stick? Everybody have a glow stick? Okay, all right. So how's it going to work? I'm going to point at one person, and that person is going to start, okay? Going to crack their glow stick and hold it up. Are you okay with that? Just one person. All right. Maybe you. Just crack your glow stick, hold it up. Shake it a little bit. And just hold it up so we can see it. All right, nice and purple. You can see it. All right, I'm going to choose another person to crack their glow stick, and then everyone around her who's adjacent to her is going to crack their glow stick. So you, and you, but not you. Okay? All right, so next round. Okay, so you. Crack your glow stick, hold it up, shake it a bit, and all the people around her go this way. Crack your glow stick. You can do it. Sorry, your arms are going to be a little tired at the end of this lecture. I'll try and do as quick as I can. Okay? Yeah, you can do it too. Yeah. All right, great. One more person. Okay, so you. Let's crack your glow stick. You do it. And then everyone around her, including who's in front and adjacent across, everyone the three behind, crack your glow stick. And everyone who is adjacent to someone who has a glow stick active, so including David, all the people here in the front, you can start cracking your glow stick.
Can it jump?
Well, you can't jump. Can't jump unless you're directly adjacent. So they're saying it's like something like COVID or Contagion.
So is this adjacent? Like jump the...
We'll keep it as a no for now. So we'll do one more. Okay. All right. Yeah, we have to determine the rules. I wasn't very good at it. Okay, everyone good? Okay, let's do two more people I'll activate just to make this go faster. Okay, you at the end, and you here. Let's crack your glow stick. And then everyone around someone who has a glow stick, everyone is around someone who has a glow stick, even if you're diagonally in front or behind, so you can do your glow stick now, sir. I know you're eager to do that. You can do it. Okay. Everyone around? Okay. Wow, that's a lot of glow sticks. That's a lot of glow sticks. Okay, is there anybody who doesn't have a glow stick? Doug, that's my spot. Yeah, do your glow stick. Oh, yes, you get one. Okay. Do your glow stick. All right, Doug has a glow stick. Everyone else who's adjacent to someone with a glow stick, do it. Just, what the heck, everybody have their glow stick out now. Lift it up. All right, congratulations. You're all burning. Thank you so much.